So here's just a nice representation of what happens to make an ionic compound. I like this picture in your textbook. Again, it shows the idea that we have sodium, metal, and chlorine gas, which are very, very different. Sodium metal is very shiny. It has to be stored under oil so that it doesn't explode and react with the water or moisture in the air. Chlorine gas is this yellow poisonous gas, very dangerous. But when they come together, when that electron pops off of the sodium and goes boop, 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 all the way over to the chlorine, then all of a sudden it becomes this miraculous thing that makes food taste great and is a good old-fashioned preservative. So looking at reactions where we make bonds, we take species, atoms, elements, whatever you want to call them, we take things and we conform them into something completely different. Here's a summary of the types of chemical formulas that we can see. A structural formula is usually what depicts the most amount of information. It's that visual picture of the compound. For a structural formula, what we see is something like H2O written out like this, where we can see the actual relationship and the bonds. A molecular formula is what we call that covalent compound in its little condensed area here, 2 hydrogens and 1 oxygen, H2O. It tells you the actual number of elemental atoms in the compound. It does not tell you how they are bonded. Notice the 2 H's are condensed there on the left, but it doesn't tell you that each one of those is generally connected to the oxygen. That's the structural formula. And the empirical formula is going to be something new. This is going to convey the simplest whole number ratio of the atoms. So molecular is the actual number, empirical is the relative number of atoms for a covalent compound. You can also do an empirical formula for an ionic compound, but let's face it, the empirical is the same thing as a formula unit for an ionic compound. Where we see a big difference with molecular formulas and empirical formulas are things like covalent compounds. Specifically, if I thought about H2O, the molecular formula, H2O, there's 2 hydrogens and 1 oxygen. That's the same thing for its empirical formula. But for something like H2O2, there's 2 hydrogens and 2 oxygens. That ratio can be reduced. The empirical formula is HO. This gets into a better idea once we start doing our determination of molecular formulas at the end of this chapter. But let's just choose another one, C8H8. This is a carbon and hydrogen molecule. Carbon and hydrogen are both nonmetals, so we can call it a molecule. In the molecular formula, it's the actual ratio, 8 carbons to 8 hydrogens. For the empirical formula, it would be CH, 1 to 1. Lovely. For, again, molecular formulas for molecular molecules, we have ways of being able to look at those outside of the structural formulas and the molecular formulas and the empirical formulas. Those are all very important. We'll focus on those. When you get into higher levels of chemistry, specifically organic chemistry, you'll have molecular modeling. We'll see a little bit of molecular modeling in the next unit. And it's very, very interesting to see how the actual structure of the atom looks in 3-dimensional space. The ball and stick model is representing atoms as balls. Why we do that is because typically when we think about the smallest shape or the smallest surface area shape, it's a sphere. And that's what we can kind of think about as all of our atoms as little spheres. Typically they're color-coded. There's not any one way to color code. This is just how your book typically color codes. It's not the only way to color code, but normally when we start seeing these ball and stick models, they'll color code the elements in the molecule so that you can see which one is which. For instance, this is a molecular formula, CH4. The structural formula shows all of those bonds. All of the hydrogens are bound with single bonds, one line to the carbon to each hydrogen. The ball and stick model, notice how it starts to look more like a 3D shape. This is where we'll get in chapter 5 and 6. It'll be very exciting. Space filling models are a little bit more accurate representation of what we think molecules might look like. But again, we won't be hanging out with those space filling models. We'll do some ball and stick models. We'll do a lot of structural formulas and definitely a lot of molecular formulas. Now, the theory behind bonding is called Lewis theory. Now, we're going to start with ionic bonding. We'll get to Lewis theory in covalent bonding. It's a little bit more complex. Ionic bonding is what we're going to start with. Now, what this predicts is the number of electrons a metal atom should lose or a non-metal atom should gain in order to attain the stable electron arrangement. We call this the octet rule. What this is going to mirror is that noble gas electron configuration. And we know that there is a completeness in filling our valence electrons. So when we think about what the valence electrons are, the S and the P, remember we have 2 electrons in the S and 6 total in the P. There's the 8 electrons, 8 for oct, 8 electrons. Now that doesn't mean that that's all that the atom can gain or lose, but it is going to just be honing in with those main group elements around the octet rule. Now, using the octet rule, the idea that 8 is our magic number, it allows us to predict the formulas of ionic compounds that result from the combination of one metal and one nonmetal. The relative strengths of those ionic bonds are also based off of Coulomb's law. So something that has a +1 and a -1 charge can be predicted. Sodium did have 1 electron, chlorine had 7. Sodium gave 1 more electron to chlorine. There's your 8 electrons total. We can always look at a +2 and a -2 charge. We're going to do a lot of practice with pulling these guys together. Magnesium is in group 2. It has 2 valence electrons. It will gladly give those 2 valence electrons to oxygen. Oxygen needed 2 more valence electrons to reach its 8 octet. Now, when we think about those 2 compounds, who's stronger? Whose ionic bond is a little bit stronger than the other? Well, think about sodium and chlorine holding hands with 1 hand each. 1 electron was transferred from sodium to chlorine. Magnesium and oxygen have a greater value here in our charges. So we'll revisit Coulomb's law and we'll be able to calculate why magnesium oxide is a stronger bond than sodium chloride. A little bit more about Lewis theory. It implies that the position of the ions in the crystal lattice are critical to the stability of the structure. We will see how it's not just the electrons transferred. Yes, the electrons are going to transfer, but another important part is building up that lattice. We'll see why that's so important when we start looking at real life calculations and what we've observed in the lab. It also predicts that moving ions out of the position should be difficult. Ionic solids should be very hard. Once they build that lattice, it's a very dense structure. And so, yes, we can react them, but breaking up an actual ionic compound just with hands or with a hammer is something that's slightly difficult. Ionic solids tend to be hard compared to molecular solids, things like water. A lot of molecules could be gases or liquids. Not a lot of molecules are hard solids. Lewis theory also implies that if the ions are displaced from their position in the crystal lattice, repulsive forces should occur. So we'll start to see why that lattice is so important to us. And it predicts that the crystal will be unstable and break apart if the ionic solid does, or the lattice structure does move or get displaced. And so ionic solids could be brittle. They're hard, but when they are struck with a big force, they tend to just all shatter apart. It also implies that in the ionic solid, the ions are locked in a position and can't move around. It predicts that ionic solids should not conduct electricity, even though there was a transfer and ions are formed. When those ions are stuck in the crystal lattice, that cannot conduct electricity. We can use an ionic solid with water to conduct electricity. However, we can't just put a light bulb in sodium chloride and expect something to happen. And when in the liquid state or when dissolved in water, the ions have the ability to move around. We'll talk about what that looks like a little bit later. And it predicts that's when the ions are free flowing and can actually conduct electricity. Very interesting. Now, I want to get into Lewis dots. Lewis theory was developed by an American chemist, woohoo, go America, an American chemist in the late 1920s, early 1930s, in order to simplify, typical American, right? Not only a chemist who wants to make things easy, but an American chemist who wants to simplify quantum mechanics. And so what he uses is this idea that valence electrons can be represented as dots. Because he said, look, we know from quantum mechanics that only the valence electrons, the outermost electrons, go into reactions. And so if I take something like hydrogen, if I just put a little dot there, there's one electron. There's the valence electron. Let's keep going, right? We have helium. Helium has 2 electrons. When we put them together in helium, it's because those 2 electrons are in the 1s2 orbital. They're a duet. They're complete. Drop down to lithium. There's its 1 valence electron. Now, beryllium doesn't have a duet. He's got 2 electrons freely on either side. Boron, 1, 2, 3 electrons. Carbon, 1, 2, 3, 4 electrons. We're again moving just across that second row of the periodic table. 1, 2, 3, 4, 5 for nitrogen. 1, 2, 3, 4, 5, 6. Notice we're just doing a merry-go-round around those elements. The reason for this is to be able to describe how many valence electrons, and Lewis brilliantly came up with this idea to say, how many bonds do these elements tend to make? Well, lithium has 1 electron, so it will give up 1 electron to become lithium plus 1. Beryllium has 2 electrons. He'll give those up to become beryllium plus 2. Boron is a metalloid. He can either make 3 bonds, like covalent, or become boron plus 3. Now, as we continue looking at all of these, what's important to note is that Lewis simplified these Lewis dot atoms in order to quickly identify a typical bonding pattern. So once we get to carbon, why there are 4 dots but 1 on each side is to understand what was typical for carbon. Carbon typically makes 4 bonds. Now that could be ionic, or it could be covalent now, right? So we could see that carbon could have a +4 or a -4 charge, excuse me, it's a nonmetal. But we don't often see that. What we start to see now as we merge over into the nonmetals is both the ionic and covalent bonding definitions could be satisfied. Now, we know the octet rule is a thing. So what we're also aiming for is how many electrons, as we merge over into this nonmetal category, how many electrons does the atom actually need to reach its octet? So not so much looking at the valence count, but 8 minus the valence count. So for nitrogen, he has 5 valence electrons, and what we see is there's 3 unpaired electrons there, 3 extra spots in order to make 3 bonds. We can also think about N minus 3 for the ion. Again, I'm only picking out the spots where there's an unpaired electron. We know electrons are paired in their orbital diagrams. And so when we're looking at these Lewis dot atoms, they're a simplistic way of truly getting to the heart of what quantum mechanics is telling us. 2 electron spaces for oxygen, so he typically makes 2 bonds, or we'll see oxygen minus 2. And there's 1 electron spot for fluorine, so 1 bond, or F minus 1. So a lot of different things with these. What we want to be able to identify is looking at these Lewis dot atoms as a simplistic way of understanding bonding, whether it be ionic or covalent. We're going to start with some of the basic ideas. Overall, atoms will transfer or share electrons to gain an octet. As we have seen in a couple of reactions so far, some elements are not by themselves out in nature. We have what we call a diatomic element. What this diatomic element literally means is that there are 2 atoms covalently bonded. So things like hydrogen, we can think about 2 Lewis dot atoms. Hydrogen will actually come together with another hydrogen atom in order to make hydrogen diatomic. Notice that this new covalent bond is 2 electrons being shared. What that does for hydrogen is it creates a duet for each of them. We can also think about writing it this way, with the 2 dots in the middle. Notice for a covalent bond that the bond is physical, it's direct. For an ionic bond, we talked about the lattice. Let's just look at another one. We'll do chlorine diatomic. Chlorine has 7 valence electrons, so we count up our Lewis dot atoms accordingly. Again, what we see is that these 2 can be shared so that we make a bond between the 2 chlorine atoms. Now, a couple of things that we'll talk about once we get into bigger structures of covalent atoms. This is, again, 2 electrons being shared. These guys on the outside are what we call non-bonding electrons. They do not need to bond because they are already paired up in the valence shell. That's something that's understood with Lewis structures. We can also call them lone pair electrons. Now, all of the diatomics that we'll see have this bonding in nature. Oxygen is another one. I want to bring up oxygen because he's a little bit different than the other two we just saw. Oxygen likes to make two bonds, and we can see that occurring. Now, when that happens, oxygen literally puts 4 electrons in between those two nuclei. This is what we would call a double bond. That is when 4 electrons total are shared. Before, with hydrogen diatomic and chlorine diatomic, 2 electrons being shared is just a single bond. Double bonds, we'll talk about what they are in terms of physical properties and how those double bonds come to existence in later units. But we should note that if 2 electrons are holding atoms together, that 4 electrons holding 2 atoms together is stronger. Just like we talked about with the lattice structure of ionic compounds, the stronger the charge, the stronger the bond. The more bonds in a covalent pair, the stronger the bond. So a single is the weakest bond, a double is stronger. Nitrogen diatomic is another one we can talk about. And nitrogen needs 3 electrons to complete its octet. So you guessed it, triple bond. The triple bond is even stronger. 2 electrons in each of those bonds, which means a total of 6 electrons shared. Now, list of diatomic that we should know. H2, N2, O2, and then all of the halogens, F2, Cl2, Br2, and I2. You should know these.